this area, Virginia Williams.
Thanks. Can everyone hear me? Yeah, great. Okay, so thank you very much for inviting me here. I'm extremely excited. And I want to mention that this talk will be about a field that basically came together in 2015 when we had a program at Simon's here about it. It was organized by myself, Mohan Paturi, Russell, who just spoke, Ryan Williams, and Daniel Marks. So I want to tell you what this is about. It's something called fine-grained complexity. So, what is it? So it's a field that was kind of coming together through the decades, and we formalized it. And in 2015, we gave it a name. How did we give it a name? So we wanted to have this program at the Simons Institute. So we started writing a proposal, but we knew what it was about, but we needed to come up with something to call it. So we sat together at a table and we started discussing it. What should we call it? Should it be problem-centric? Should it be this? Should it be that? And I said, what about fine-grained? And then we're like, oh, I don't know. It doesn't quite describe it, but it's okay, you know. And then eventually we said, okay, let's go with that. That's the best we could come up with. So there we go. Now it's fine-grained complexity. And what is it about? I'll tell you about it in the next few slides. Okay, what's the motivation? So we like to design algorithms, right? Okay, so what do? We look at some computational problem, some problem A, and we try to come up with an algorithm. We have a lot of these techniques, we put them together, and we come up with some algorithm, and we analyze it, we get a running time A of n. And then we think, is A of n the best we can do? Well, maybe not. And then we start shaving polylogs, okay? Maybe we shave a little more than a polylog. And now I don't mean a polylog in n, the input size. Does this work? I don't know. Well, it doesn't. Well, anyway, we shave polylog in the running time. So for example, if your running time is exponential, you'll be shaving polynomial factors or maybe sub-exponential factors. But in the end, we get stuck. For many of these problems, we can't seem to do much better than A of n. So we can't get A of n to the 0.9999. Okay, this is a conundrum. It keeps happening over and over and over. There's a lot of these problems. You end up shaving polylogs, or sub A of n, but not A of n to the point something. Okay, so I'll give you 3 examples in this slide, but you can come up with so many. They're all over the place. So what is one of our favorite? Well, our favorite problem, K-SAT, right? We have a KCNF formula on n variables. We want to know, is it satisfiable? How do you do it? Well, you brute force. Try all the possible Boolean assignments, plug them in, and you get a 2 to the n time algorithms times a polynomial. That's what that star hides. The polynomial is just evaluating formula. Okay? You can do better. If the clause width is constant, you can actually do better than 2 to the n, but see here is some constant, and people work really hard to improve on the constant over there. But for whatever reason, there's no algorithm known that gives you such a running time here, an improvement over 2 to the n in the exponent for some epsilon bigger than 0 that works for all the case. Okay, and so that's where we're stuck. Okay, here's another problem, completely different. You have 2 sequences over some finite alphabet, and you want to know what is the longest sequence that appears in both of them, the longest common subsequence. This is a problem we teach in our algorithms classes. It's a prime example of dynamic programming. You can you write a dynamic programming table, you get an n squared time algorithm. And people have tried for a long time to improve over n squared. Messick and Patterson got n squared over log squared of n. That's the best known. So we shave polylogs, but we don't have n to the 1.99. So again, it's like some function to the 1 minus epsilon, which is what we can't get. And there's another one. This is from the graph algorithms community. Again, we teach it in the undergrad algorithms classes. We have a graph that is given on n vertices. You can think of it as dense. You know, it could have integer edge weights, and you want to compute all the shortest path distances. There's n squared of them. And if you run Floyd-Warshall, you get n cubed, an n cubed time algorithm. If your weights are non-negative, you can run Dijkstra from every node. Again, you get n cubed. Ryan Williams was able to shave a lot of logs, in fact, all the polylogs. So he got n cubed over 2 to the square root log n, but unfortunately that is not shaving a polynomial. So we still don't have better than n cubed in this sense. So as you can see, we have this sort of the same story, and this happens all over. Okay, but what can we say in complexity? Well, we know, well, this problem is very famous. It's NP complete, right? That means if we believe P is not equal to NP, this problem will not have a polynomial time algorithm. So it's hard, right? Except it's not as hard as we want it to be hard, or maybe, you know, we believe it to be hard. So there's a huge gap between polynomial and 2 to the n. So NP completeness says nothing about improving over brute force search here. It also has this other issue, but these problems here are already in polynomial time, so they're not NP complete unless P equals to NP. So NP completeness is not going to tell us anything about why we're stuck on those, but yet is the same sort of phenomenon happening for all these problems, and we want to know, are we actually stuck for the same reason? Maybe we are, maybe they're all equivalent in some sense, right? Could be. So that's what we want to answer in fine-grained complexity. Okay, so how do we do it? So we want to kind of mimic NP completeness. So we're going to come up with some hardness hypotheses, kind of like P not equal NP, except for a variety of reasons, we end up needing more hypotheses, and they're problem-centric, as you'll see. Then we take these key hard problems and their hypotheses, and we reduce the problems in some specialized ways to all the problems on which we're stuck on. And I have to tell you what the reduction is, and I will. And then in the end, we hope to show that they're all equivalent. We're not there yet, but we have equivalences. Okay. And the interesting thing about the equivalences is that they're about problems that have different running times sometimes, which is nice. Okay, so good. So first I'm going to tell you the 3 or 4, depending on how you think of it, key hard problems that we focus on and the hypotheses that come out of them. So the first hard problem is SAT. And there's a very nice hypothesis, the strong exponential time hypothesis, about SAT, which basically says that for every epsilon, there's some clause with k for which you cannot solve k SAT in 2 to the n to the 1 minus epsilon time. And this hypothesis was kind of hinted in a paper by Russell and Paturi and Zane in 2001, but actually wasn't named until 2010. So we cite Calabro and Polezzo and Paturi from 2010, even though it's older. So we use this hypothesis to explain a lot of stuff. And it turns out that there's another problem in polynomial time that's really related to this. This is this orthogonal vectors problem. So here you're given a set of n vectors. They're very short, of dimension d. D is polylog n. Think of it, it has to be at least log n. And they're binary, 0, 1. So think of this as a version of set disjointness. Think of having n vectors over a tiny universe of size d. What do you want? You want the vectors to be orthogonal. You want to know if the set contains 2 vectors that are orthogonal. In the set disjointness world, you want to know if the set of sets contains 2 sets that are disjoint. Okay, so it's very easy to solve this problem in n squared times d time by taking every pair of vectors and computing the inner product. You can do a little better if the dimension is log n. You can do better than n squared, but this is basically shaving polylogs, shaving stuff. So there's a hypothesis that says that this orthogonal vectors problem is really hard. It essentially requires n squared time. I forgot to mention, we always have to fix our model of computation because we actually care about exact running times. So I'll fix it to the word RAM model of computation with an order log n bit word size. So a nice paper by Ryan Williams in 2004, 2005, the journal version is 2005, shows that if you believe the strong exponential time hypothesis, you better believe that orthogonal vectors is also hard, because you can reduce SAT to orthogonal vectors in the sense that any n to the 1.999 time algorithm for orthogonal vectors would give you a better than brute force running time for SAT. You'll get 1.999 to the n for SAT. So in fact, we think that even if the strong exponential time hypothesis fails, this orthogonal vectors problem could still be hard. So there's some reasons to believe. But anyway, there's these two problems, and often the reductions that we get from SAT actually go through some orthogonal vectors or a version of it. Another problem that comes from algorithms, of graph algorithms, is all pair shortest paths, as I mentioned earlier. And the associated hypothesis is that all pair shortest paths on dense graphs on n nodes, even when the edge weights are integers between 1 and n to the c is 100, let's say, this problem requires n cubed time, n to the 3 minus little of 1 time. So this hypothesis was kind of swimming around in the graph algorithms literature. People said, oh, we don't know if we can solve this problem very fast, because otherwise we'd get a better than n cubed time algorithm for all pair shortest paths, and we have no idea how to do that, so it's hopeless. But that nobody actually named it, but we did. So there we go, the all pair shortest paths hypothesis. And here's another hypothesis. This is from computational geometry. There was this very nice paper by, I can't pronounce this name, I'm sorry, Gayentan and Overmars. Okay, so they had this paper that said that if this threesome problem requires n squared time, then a huge number of computational geometry problems would be hard in a sense. So what is threesome? You're given a set of n numbers, integers here, and you want to know if 3 of the numbers in the set sum to 0. Of course, you can solve this in n squared time. N squared log n is super easy. You just try every pair of numbers in your set, hash their sum, and then check for the other numbers if the negative the numbers in the set. But you can also do exactly n squared, and doing better than n squared seems hard, but you can shave a polylog over there, and the hypothesis says you can't do better than n squared. For the original paper in 1995 said that you actually can't do better than n squared even by polylog, but that was refuted by that 2005 paper. And now our new fine-grained hypothesis is that you need n to the 2 minus little of 1 time. And these are the main hardness hypotheses we use. Why is there not one? Because we cannot show that they're equivalent. And there's some papers that suggest that maybe they're not equivalent. Okay, so that's what we have. You can add many, many more problems and hypotheses if you want, but these ones already explain a whole lot. So I would just focus on these. So now I'm going to tell you what a fine-grained reduction is. So we can't just use any sort of polynomial time reduction. We have to be more careful in how we define reductions. So let's define what reduction will mean. So we have two problems A and B, and some running times A of n and B of n. And you want to say that improving over B of n for B would improve over A of n for A. That's what our reduction should imply. So here's how we defined it in 2010, if you think about it. So we say that A is AB reducible to problem B if for every epsilon, there's some delta. So, and an A of n to the 1 minus delta time algorithm that looks like this, it runs in A of n to the 1 minus delta time. It solves a problem, an instance of problem A using oracle calls to problem B. But the sizes of the calls could be different. And the only condition is this red inequality over there that says that the sum of B of n sub I to the 1 minus epsilon over all these instances I over here is less than A of n to the 1 minus delta. What does that mean? It means that if there exists some epsilon bigger than 0 so that B can be solved faster than B of n time, in the sense that order B of n to the 1 minus epsilon, you can take that algorithm and replace the oracle calls with the run of the algorithm. Then you can solve problem A in a running time, which is the reduction running time plus that sum over there, which is the sum of the running times of all the instances that your algorithm created. And then you will get that if for some epsilon, B is in B of n to the 1 minus epsilon time, then there exists some delta so that A is A of n to the 1 minus delta time. Epsilon and delta could be different, but the point is that if epsilon is bigger than 0, then there's some delta that is also bigger than 0. So improving over B of n substantially, you will allow you to improve over A of n substantially. And this is the key definition that we needed, because now you can show equivalences that are more flexible. You don't want to have equivalent, if you only restrict yourself to equivalences where the running times are exactly the same, you won't be able to prove as much as when you allow flexibility here. And yeah, we can prove very interesting equivalence. Okay, so this is maybe the most technical thing that I'm going to say today, but I want to flash a slide over here with a bunch of stuff people have shown. And this is definitely very far from complete. There's so many papers that have happened since I first drew this slide. From threesome, as I said, that there was this huge literature in computational geometry, where if you assume threesome requires n squared time, then a lot of problems in computational geometry also require an n squared time, and a bunch of problems in sequence alignment also require n squared time. If you go from K-sat and go through orthogonal vectors, you can show that a lot of problems also require n squared time and other running times. For all pair shortest paths, we have a bunch of equivalences. So all pair shortest paths is, for example, equivalent to finding the shortest cycle in a graph, or computing the length of the shortest cycle, and things like this. And also, there's a lot of problems that you can show hardness for from all three. But this is an ever-growing field, and we're learning more and more, and we're still trying to see whether these three are equivalent. Now, what I'm going to do for the rest of the talk, I'm going to tell you how orthogonal vectors and K-sat that give you something for the graph diameter problem, something very interesting to me. So let me show you that. Okay, this is about graph diameter approximation. What's the diameter of a graph? So imagine we have a graph. It could be directed or undirected, weighted or unweighted. We'll focus on undirected, unweighted, because it's the simplest. D of UV is the shortest path distance between U and V, where U and V are vertices in the graph. The diameter is the largest shortest path distance, so the max over UV of DUV. And we want to compute it, okay? How do we compute it? Well, we can compute all the pairwise distances of the graph, right? And take the maximum. So we solve all pair shortest paths. All pair shortest paths is a very computationally intensive problem. So if your graph is dense, as I mentioned, Ryan's algorithm runs in n cubed over 2 to the squared log n, which is very slow. If the graph is unweighted, I give this as a graduate exercise in my class. You can do n to the omega, the matrix multiplication running time, and you can solve the problem then. Very slow. For sparse graphs, you can do a little better. So Petty showed that you can do mn plus n squared log n. M is the number of edges. If the graph is unweighted, of course, you can run BFS from every node. So you get mn. So let's focus on very sparse graphs, where m is essentially n polylog n. So that's what that all tilde is. Then all pair shortest paths runs in n squared time, n squared polylog n time. And the output of all pair shortest paths is n squared distances, whereas the output of diameter is one number. Why do I need to spend n squared time to find one number, right? Do we need it? And what if we settle for approximation? Okay, so let me talk about approximation very quickly. Here's a folklore algorithm for approximating diameter. We're in the world where the number of edges is basically n, the number of vertices. let A and B are the endpoints of the diameter path. So there's some two vertices so that their distance is the diameter. We don't know A and B, okay? We would like to know them. So there's A and B, their distance is D, D is the diameter. What we can do is we can pick an arbitrary vertex V, right? And run BFS from V. There we go. Then we output the largest distance that we found, the maximum over all the distances from V to every node U. So in particular, the algorithm will consider A and B, right? Okay. Now, this looks like a triangle, even though it's wavy. So we're going to use the triangle inequality. If the distance between V and A is less than D over 2, then the distance from V to B must be at least D over 2. Otherwise, the distance from A to B will be less than D. Okay, so this means that what this algorithm outputs is something that's at least D over 2, and is at most D because it's a distance. And the running time is basically linear because you run one single BFS. And it's super simple, but why can't we get a 1.9 approximation in linear time? Why do we get 2? Why can't I get 1 plus epsilon approximation in linear time? So that's a question we would like to answer, and this is what fine-grained complexity gives us an answer for. So here's two algorithms. You can read this, but it's better to look at it in a picture. Here's the picture. So remember, we're in the sparse world where the number of vertices and the number of edges are the same. On this axis is going to be our approximation factor. It goes from 1 to 2, because we know that 1 is an exact answer, 2 is a 2 approximation. Here we have the exponent of the running time. Okay, so n to the c, where you a c so that you can get an n to the c time algorithm. Over there, that red dot is the algorithm that computes all the distances in n squared time. It's an exact algorithm, runs BFS from every node. Here's that algorithm on the previous slide where I run BFS from a single node. It gives you a 2 approximation. Here there's another red dot that we obtained, Leon Rodity and I got in 2013. It's an n to the 1.5 time algorithm that gives you a 1.5 approximation. And then there's these many dots over here that only work for undirected graphs by a paper by Cairo, Grossi, and Risi. And basically they go to 2, the approximation ratio goes to 2, but it's basically 2 minus 1 over 2 to the k. So it's not linear, it's like an exponential sort of decay to 2. So are these the best possible algorithms? I don't know. Okay, but this is what we're going to answer. How do we answer it? Well, it turns out that you can go, and I'm not going to prove this to you, but it turns out that the answer is to look at a version of orthogonal vectors called K orthogonal vectors. So orthogonal vectors is, as I said, as you're given a set of vectors, you want to know if 2 of them are orthogonal. In K orthogonal vectors, you're given a set of vectors, you want to know if K of them are orthogonal in the sense of generalized inner products. What it's asking is it true that for every coordinate, at least one of the vectors is 0 in that coordinate, right? Okay, so that problem requires n to the k time if you believe that the strong exponential time hypothesis is true, and that kind of follows by an argument that Ryan made a while back. So now we have this problem that it's parameterized by k, and you have n to the k running times, and you use that to create some reduction, and I'm not going to tell you exactly what it does, but basically you take your k of v instance and you create a graph whose size is n to the k minus 1, but you're trying to beat an n to the k time algorithm. So you're getting some running times that approach linear time as k grows, and you hope that the approximation factor you want to beat goes to 2. So that's a bunch of words, so I'm going to show you a picture. There's a picture. And the theorem we showed in last year was that for every k over there, there is, if you have a very fast algorithm, an n to the 1 plus 1 over k minus 1 minus epsilon time algorithm that gives you a 2 minus 1 over k approximation, then Seth is false. So what does that mean on the picture? It means that you can draw this step function over here that nicely goes through all the 3 red dots, the 3 algorithms we have, and it shows that there's no algorithms underneath that line. So that means that all these red dots, these red algorithms, they're optimal under strong ATH. In particular, you will not be able to get a better than 2 approximation in near linear time if you believe the strong exponential time hypothesis. Okay. We didn't get this from the ether. Okay, so how did it come up? So in 2013, Liam Rodady and I observed that you can easily reduce orthogonal vectors to distinguishing whether the diameter of a graph is either 2 or 3. So that showed this dot in a sense is optimal. So in the sense that if you want a better approximation, your running time goes to n squared. Then in 2018, with Bakhurs, Rodity, Segal, and Nicole Wine, we showed that it's optimal in the other sense. So if you want to improve the running time, your approximation factor goes to 1.6. Then Ray Lee said actually it goes to 5/3. Okay, he improved a little bit. Then Bonnet in 2020 showed that if the running time is n to the 4/3, then the approximation factor blows up to 7/4 or something. And then we finished it up. But how? First, Ray Lee and my students, Mina Dali-Ruifard and Nicole Wine, did it for directed graphs by adding some directed edges in the gadgets. And then we were stuck for a long time because directed edges really help. And then we could create a completely different construction that also worked for undirected graphs. But in the end, what that shows is that with fine-grained complexity, you can show that you can get these approximation running time trade-offs, and you can show that they're optimal. And what's left over here is to bring these orange dots down and show that there's algorithms at every step over here. And that's what we're working on right now. So I think that's true, but we got to work on it. Okay, so that's all for diameter. And I have one more last slide that keeps you away from lunch. Okay, so here's the last slide. It's on a few extra developments. So what else has been happening? So there's this trend to try to develop something called fine-grained cryptography. So what is that? Imagine that for some reason P equals NP. Then are we dead? Maybe everything is gone. Well, maybe we can still have some sort of weak notion of cryptography that could still work out. And so then you would say, well, maybe even if P equals NP, maybe 3 sum still requires n squared time. Or maybe all pair shortest paths still requires n cubed time. We don't have a way to show that these things are related. And then maybe we can still salvage something out of this. And so there's been this work by Ball, Rosen, Sabin, and Vasudevan that started this field saying, let's build cryptographic protocols from fine-grained assumptions. And we had a paper along these lines as well. But then it kind of requires that you have worst case to average case reductions in fine-grained complexity for the fine-grained problems. So the original work developed these reductions where you take these fine-grained problems like 3-sum orthogonal vectors and then create these other specialized polynomial sort of problems, algebraic problems that are hard on average, and you can plan stuff in them and so on. And then we try to get some more combinatorial looking problems, but we weren't quite there. And so what we would really want to show that the original fine-grained problems are hard on average, but that turns out not to be true for some of them, for example, for orthogonal vectors. So interestingly enough, all these problems are about counting problems. So what about looking at counting complexity? We know that for a lot of problems, for example, for graph matching, when you start counting the objects, the problem becomes super, super hard, right? So what about the problems that we have? 3-sum all pair shortest paths and orthogonal vectors. What if we want to know how hard they are to count? Okay, so there was some work by Dell and Lipinskas, and also Dell, Lipinskas, and Meeks that showed that approximate counting is equivalent to decision. Okay, so maybe that's not that surprising. However, in some very bizarre work that we just had with Timothy Chan and my student Yin-Jan Xu, we showed that 3-sum, for example, is equivalent to its counting version. Doesn't make any sense to me, but it is true. So if you can count the number, if you can decide whether there's a threesome solution, you can also count the number of threesome solutions in subquadratic time. What does that mean? We still don't know, but we're thinking about it. So anyway, that's all I wanted to say. Thank you again for having me.
Questions? All right. Looks like we'll take the questions at lunchtime. Thank you, Virginia, for a nice time.